My name is Bill Tong. I'm the Vice Provost, and Provost Ochoa has an unexpected scheduling conflict, so he's not here, and I'm very happy to be here to welcome you all to this very special event, 2022 Albert Johnson Lecture. As you all know, Albert Johnson Lectureship is our highest honor, research honor at SDSU, and only one outstanding SDSU professor is selected every year for his or her outstanding research accomplishments. And we have been honoring outstanding research with this award since 1984, the last 38 years, about the time I came here as a chemistry professor. We were just talking about it on a personal note. When I delivered this lecture 17 years ago, my mother attended, and that was the only time she came to SDSU in 37 years. And I'm glad Chris's family is here in the back. So due to the pandemic, a 2021 honoree was not selected last year, and also the 2020 recipient did not get a chance to present her talk. So I'm very happy to introduce her today. And when the 2020 honoree was selected, she was a faculty member at the School of Public Health. But today, she is the interim vice president for the Division of Research and Innovation. Please join me in congratulating Dr. Hala Madanath. Now, I'll ask Dr. Madanath to introduce.
Well, maybe we should ask our fellow distinguished faculty to stand up that are present today.
I see a few of them here, so please stand up. Sam, Eugene.
And Bill.
Oh, yeah, me and her. Thank you.
Thank you, Bill, for introducing the award. But I get the honor today to introduce our awardee, so Dr. Chris Mee. And I really don't think he needs an introduction to most of you, but I still will. You may have read his work in Wired, or heard his interview on KPBS, or read other articles that he has written about flying taxis or futuristic renewable energy grid. Chris is truly a prolific researcher. Since coming to SDSU, he's received almost $6 million in research funding, and he's published more than 200 research articles in peer-reviewed journals, and has 25 either pending or accepted patents. So an incredible researcher. He's also recognized by his professional organizations. So he's a fellow of IEEE, which is the Institute of Electrical and Electronics Engineers, as well as the Society of Automotive Engineers. And for all of you, I'm sure you know that these organizations are really selective in picking fellows. It really is a reflection of an individual's career and contribution, innovation to their fields. He's currently the director here at SDSU of the U.S. Department of Energy-funded Gates Center for Electric Drive Transportation. What I love about his work, though, is the translational aspect into real world. So his work in the wireless power transfer theory and technology, it's been adopted as an international standard for wireless vehicle charging. And I think that one of those days, we'll all be getting around seamlessly in wireless charge electric vehicle, thanks in part to the research and the work that he's been doing. And I want to share a couple thoughts from his colleagues. So his nomination package was incredible, and the reason he was selected, obviously, by his colleagues The nomination package reflected on other areas that Chris contributes to. These include his teaching. So one of his colleagues, Dr. Sarkar, tells us that the students really enjoy his teaching. And so beyond being a prolific researcher, he is also recognized as an incredible, distinguished educator and outstanding educator. His collaborator, Dr. Wood, calls Chris one of the hardest working people I've had the pleasure of working with. He has the unique ability to be a fantastic project manager and a brilliant scientific mind, and a unique combination that makes Chris a cut above the rest. And if you think about that, that's truly incredible combination of skills. Most of us as scientists don't translate into the project management aspect of our work as well as easily. But beyond all of that, I think one of the things to know about Chris is that he's an inspiration to the rest of his colleagues. Since he assumed the role of chair for his department, he has recruited outstanding young faculty into the department and has over doubled the grant procurement for his department. So Chris is an accomplished researcher. He's a dedicated mentor, and he's an admired leader across the campus, nationally and internationally. But before I ask him to come up here and give us his incredible lecture that I can't wait to hear, I'm going to show a short video.
If I go back really to the early days of my life, my hometown did not have electricity until the late 1990s. So I grew up there with an oil lamp for many years, reading and the oil lamp. Until I got to high school, where they did have electricity. It was amazing. So I thought, maybe one day I'll be able to study electrical engineering and build some sort of power generation that will help to bring electricity to those villages. The humanity is facing a number of issues. So global climate change, for example, is one of those. So the work that I do related to electric vehicles partially helps solve those problems. Battery management and wireless charging, it helps address the safety, the convenience, the range of electric vehicles. So overall, it's going to help to mitigate some of the issues we're facing today. So the idea that we have to get electricity from cable, it's been an old concept. In a nutshell, is that we can transfer electricity over a distance without a cable. It is very much similar to a wireless signal that we use on our cell phones. The pickup device on your car is able to pick up the electromagnetic field. From there, it's generating electricity. What got me excited is that I see the technology we develop gets used by the general public. That's really exciting. As a professor, I think the most exciting part is to work with a young generation of students every year for the rest of your life. It's very exciting. Thank you.
Go.
Oops, sorry. Let's get this over to the... Oops. Oh, okay. Okay, I am truly very excited. Thank you so much, Vice President Madanet and Dean Eugenlowski and everybody. Thank you so much for joining us for a very special occasion, and I'm very humbled to receive such a great honor. While I was preparing the lecture, Kelly, our communication director, asked me, do I have any pictures of my childhood? I said, well, this is not me, but this is sort of life I experienced. I was born and raised in a remote area. We didn't have electricity until the 1990s. I didn't have any picture taken until I graduated from high school, where I took a small picture to put on my entrance exam certificate. That's the only picture I had before I joined college. So anyway, I was asked to talk about wireless power. I thought I wanted to start my lecture by asking maybe just a simple question. Anybody know what this device is? Pacemaker. Guess it. What is it? Pacemaker. A pacemaker, right. Good, a pacemaker. So wireless charging is something that has been going on for a while, but it's only got very exciting in the past few years. When we walked here today, it was very typical that my computer won't last very long, the battery won't last very long, so I needed to find a cable to connect my computer. And both Bilton and Hala got tripped almost over on this cable. So would it be nice that we can have wireless on this table that I put my computer here? I have never to worry about charging my computer, right? So that is something we're doing. And this pacemaker is a pacemaker. It's something that people put in their heart when the heart doesn't work properly. And we have to do a surgery to put it. And this little device generates electrical pulse to excite the heart when the heart is not functioning properly. So in order to generate that electrical pulse, we need a battery in it. What happens when the battery runs out? Guess what you can do with it. Now, of course, in the early days, the device was started in the 1960s. The first person got this device only lived for about 9 months, which wouldn't be an issue because the battery will last that long. However, later on, you find that people will live for more than 20 years. And the battery only lasted about 5 to 6 years at that time. Now, it is probably better, but still won't last 20 years. It will last about 10 years. So the only way right now, even today, is to do a surgery, replace the device, or replace the battery. So you can think about the painful operation that you have to do, right? So with that, I'm going to just explain to the general audience. I know many people here are not electrical engineers, so I want to make sure that I explain very well so you understand what I'm doing and why it's important. So I'll start with what is wireless power, why we have to do research on wireless power, and how is it transferred, what is the history, how have people done in the past, and what is the method that you use, and is it safe? I got asked it quite often. People say, if I buy one, would it be safe? And what are the applications that's going to be for wireless power? And then I'm going to post some resources. Anybody who is interested in learning more, and then there's a YouTube link that you can go. And I also, at the last, talk about other research topics that I do in my research group. So what is wireless power? Well, basically, just think about when you make a phone call. Right now, most people use wireless phones. But go back 15, 20 years, we're using landline. So the landline transfer information over a cable, and wireless phones receive information from like electromagnetic field. So wireless power is similar. If we have a tower, some sort of transmitter, then we can have all sorts of receiver to receive energy. So there's no need to plug in a computer, a phone, a drone, electric vehicle. You can think about it. So basically, wireless power is transferred through air or through water or any other media, but no need for cable. So that is the definition of a wireless power. And then why do we want wireless power? Well, I already illustrated today, if there's wireless power, it would be much better. Nobody will get tripped over. So that's safety is one. Think about somebody or yourself. Here we probably don't see that, but I lived in Michigan for 15 years. In the winter, you got icy, you got snow. Charging your vehicle can be quite a challenge. And the cable can get old, crack. And also, it's interesting that a couple of years ago, I was in London. My friend drew an electric vehicle. He got a cable in his trunk, pretty dirty, because when you think about the cable, put it out and put it back, I said, why would you put your cable in the trunk? Well, he said in Europe, in here, if we leave the cable on the charger, people are going to come and cut it for money, to sell for money. So we have to put it in the car. So it's inconvenient, right? And secondly is that convenience. Look at that cable that it tangles and on everybody's desk, and you go to rural areas in India, for example, a lot of pictures showing all kinds of cable all over the place, not safe. Also doesn't look nice. And finally, it's productivity. For example, if you have a vehicle that are running on a pot to move goods around, so over time the battery is drained, what you have to do is you have to move the vehicle to charge somewhere for a couple hours before that vehicle can be used again. With wireless charging, you can operate the vehicle at the same time the vehicle is charged. So therefore, we don't have to stop. It increases productivity. And later on, I will give you another example, which is also critical. So those are the advantages that we do it. And then how do we do wireless charging? Well, again, as I mentioned in the very first slide, it's very simple. For a vehicle, we need to build a transmitter, and then we build a receiver. So the receiver on the vehicle and the transmitter on the ground. When we park the car on top of the transmitter, the car receives the energy. So very simple, as long as we can design the transmitter and the receiver properly. And another example, if it's not going to happen for all the highway, but some sections or some rest areas where you have this wireless charging built, and then we can have a vehicle driving on that track, receiving power when the vehicle is driven. So we don't have to stop the vehicle for charging. And finally, of course, many people already have this wireless charging device for your phones and laptops. So that's how you do it. So looking at the wireless power, when I step in, our previous Vice President, Steve, to ask me, how long have this been there? Have been people developing wireless charging in the past? Yes, wireless power, the concept itself is not new at all. Even over 100 years ago, Nikola Tesla, which is one of the smartest person on earth, have developed wireless power. The only problem that he didn't have all the technology he needed to make it work. So if you look at the history, in the late 1800s, Tesla is the very first person to design a Tesla coil that actually was able to transfer power over a distance. And later on, he got really crazy about it. He said, I'm going to build a tower. That's the one you see over here, 1899. He built a tower this is now all called Tesla Tower. And he wanted to transfer electricity from this tower so that people all over New York can get power without a cable. Because think about the time electricity just started. They didn't have cable buried in ground or overhead. So they got cables all over the place. Didn't look nice. But unfortunately, this was probably the hardest thing that he did. Was not successful. He had to declare bankruptcy because of this work, spending a lot of money. So it was quiet for many years. It was a little work done here and there in the 1960s, 1970s, 80s, but it was not until 2007 there's a group of professors, researchers from MIT physics department did an experiment that's on that one, light up a lamp over 2 meters of distance. That really spiked interest in the research community, and we were the ones also following that. So from that point, we did our study. As Harlan mentioned, some of the topologies, some of the circuits that we developed is being adopted by a Society of Automotive Engineers in their wireless charging standards. So you might be asking, Tesla was a so smart person, why was he not able to make it work? Well, the fact is that he didn't have all the technology we have today, even though he was smart, but he didn't have the tools to do it. The tools, you can think about it. Why didn't we have a cell phone 30 years ago? Because we didn't have all the microchips we have today. The power semiconductor devices only work since the 1970s, not very long ago. Magnetic materials, lead wire, it's a special kind of cable, didn't exist at all. And then control technology, control algorithms that we developed. Well, bottom line is that people want it. Why we have washing machines, why we have dryers, why we have this or that, because people want it. So that made it happen. So how do we do power, what kind of method we do wireless power? I can mention a few. Many of you will resonate. For example, electromagnetic induction. This is very simple. When we were in high school, when we were a little kid, we use a magnet to track something. Well, actually, it works in mining, for example, they use induction to heat up metal so that you can separate different metals. And then radiations. Radiation is very popular. Microwave, for example. How many of you don't have a microwave at home? Everybody has one nowadays. And then finally, it's actually the category we're working on is the electromagnetic field resonant that we do for high power wireless power transfer. So now let me get into this topic. Is wireless power safe? Even with wireless phones, I think there's still debate whether it is safe. Is it going to cause brain cancer or something else? So it's very hard to answer that question. To answer that question, we did a very complicated study to demonstrate that this thing actually is safe. So we did this in terms of a human. So basically, we took an electric vehicle charging system. We look at, because somebody is saying, very curious to look at what's happening. Is there wireless power? Can I see it? Right? That's what happened. And then we look at small animals, and also we look at metals. We know that I mentioned already, metals can get induction inside the electromagnetic field. So we did this study. So we look at the human. Basically, the way that to look at whether it's safe is only we can look at some international standards. Right? So we look at the magnetic field and the electric field. So those are the two fields at high frequency that might cause like heating, tissue damage, maybe biological changes, neurological changes, or things like that. So we look at the magnetic distribution and also the electric field distribution. So on the left hand, it's a magnetic field. On the right hand, it shows electric field. And when we look at the field density, for example, it's 1.36 Tesla. It's very abstractive. What does it mean? 1.3 micro. It's very small, right? So in the middle, we look at the two different standards. So one is from both are international standards that was built for something else. So we look at those have guidelines. For example, the magnetic field has to be less than 27 microtesla. Okay, so all field is only 1.3. Apparently, it is safe, right? So, and the E field, similarly, they say it has to be less than 83. Or all field strength is 2.83. So that is quite good. And then we look at what happens if somebody sits in the car while the car is being wireless charged. So this happens, for example, husband and wife going to shopping. Wife said, I'm going shopping. I said, no, I'm not going. I'm going here to get some work done. And while the vehicle is being charged. So we look at it, the magnetic field, again, and the electric field, they were both way below the international standard with our law. So this basically says, yes, we think it is safe. And then second, we look at animal, what happened, because when the vehicle is charging, there's a space between the vehicle and the ground. And this is sort of not your wireless phone charging, but on the electric vehicle charging. So if a small animal is able to crawl there and sitting there, it might cause damage. We don't know. So the only way to look at it is to do a study on this. So we modeled this small cat, and we found that the electric field strength is getting up to 1156 microtesla. So this number is quite dangerous. The reason is that I had high frequency with the water and the blood all inside the body of an animal, it can warm up the animal. So if the animal stays there and went to sleep, for example, and this animal will be warm up for, say, from the normal temperature to about 45, 46 degrees, it will kill the animal. So that's something that we don't want to happen. So, and then since this is a problem, we'll have to develop a technology so-called foreign object detection. So we need to detect if there's an animal there, we got to stop charging, or we have a way to get the have the animal move away from the charging pad. And finally, on the safety study, we were testing some metals. And we did both simulations as well as testing. By the way, we didn't do animal testing, so don't worry about the animal subject. We only did simulations. And then this is the study, actual testing using metal. And as you can see, because the high frequency electromagnetic field, when we put metal in the charging area, the metal will get heated up very quickly. In fact, in about a couple of minutes, even it can be as small as a nail, the temperature will go around 120 degrees C. So if it's there for about 45 minutes, 1 hour, you can imagine that this thing is going to blow up. So charging a vehicle with metal in the charging surface area is not going to be safe. Especially think about a scenario in the fall, you park somewhere, there's a charging, there's going to be leaves. On the surface, you'll never see it. Then there's metal actually buried inside the leaves, and then you go work, you're charging. When you come back, your vehicle is gone. It's blown up by the fire, right? So then, yes, so it is a problem, and people are working on developing foreign object detection technology to mitigate all these issues. So being a professor, I have to talk about technology so how does it look like on a wireless charging? It's actually, I said about the transmitter and receiver. In fact, it's not that simple, because building a transmitter is not just sort of putting some bunch of wires, it's going to transmit. Actually, we have to get many parts put together. So starting from the wall, getting the AC rectified into a DC, and then converting that DC to another DC. You don't ask me why. There's a need to do that. And then converting that DC into a high frequency AC. The AC that we get from here is 60 hertz, but the frequency in our system is at 85 kilohertz or even higher. And then from there, you provide the AC into a transmitter, and then above that, there's a receiver. The receiver gets power, and then that's converted by another device called a rectifier. From there, you get DC to charge the battery. So we have to design many parts of the system to make it work. And also, there's communication between the car or the charging, any device while it's charging, because the receiver and the transmitter, because there's a communication to make sure that it knows when to start, when to stop. You don't want to overcharge the battery, right? So that's what happened. There's also some experiments set up in our laboratory. On the, left hand, you see there's a setup, and then on the right hand, there's early setup. On the bottom of the plywood, it's a transmitter. On the top plywood, there's a receiver. And we do measurement, we do power. So what happened with this experiment? As you can see here, we have the transmitting the power at 7.9 kilowatts, and efficiency was 95%. So why I mention efficiency? Because efficiency is critical for any power transfer device, wireless or wired transfer system. Because any loss between the 100% and the efficiency, that's a loss. Any loss in the system is transferred to heat. Once it's transferred to heat, we have to be able to dissipate. And a lot of people don't have an idea or concept how much heat and why is it important. I mean, I want to ask you, some of you might use electrical stoves at home. You know how many kilowatts on that each of the cooktop? You got 4 of them, 4 coils. The small ones, the big ones. The big ones are around 4 kilowatts. The small one is around 1.5 kilowatts. So that's kind of power you look at. So if you look at a Tesla Model S or whatever Tesla vehicle, and you want to fast charge the vehicle, now they offer you up to 240 kilowatts of charging. 240 kilowatts. If you look at, let's say, 5% loss on in the charging process, how much loss we generate? So 5%, 100 is 5 kilowatts, 200 is 10, and 250 is 12.5. 12.5 kilowatts is the total of your cooktop that you turn all 4 on. That's going to make it really hot. So that's why it's important. So when we do the testing, we want to make sure it's charging, because not everybody can park the vehicle at the center of the transmitter. What happens if somebody park on the right, left, front, left, rear? So we did testing on this one. We look at the car, it's parking 300 millimeters to the right. And we found the power drop from 8 to 4, the efficiency drop from 96 to 95. And then we increase the distance. If somebody drive SUV in comparison to somebody drive a passenger car, right? So the height is different. So we look at the power will continue to drop, efficiency also drop a little bit. The good thing is that the efficiency didn't drop that much. So this is technology that we developed. It's been adopted by the international standards. And one of the recommended circuit is not the one circuit, but some of the recommended practices. So next, I want to talk about, I mentioned electric vehicles a lot. So that's one area of application. And often we have issues to deal with, like safety I mentioned earlier. Also, there's added cost to equip one electric vehicle with wireless charging. So that may not be practical for some people who didn't want to spend the money. So here I give a list of things that might not be an issue. So safety may not be a concern. There's reasons for that. And also cost may not be an issue because that investment can be recovered from the savings that you get from the system. The first example is an electrical bus. Electrical buses becomes more popular in populous areas like India and China, Europe, all those places. They're starting to deploy electric vehicles. Actually, in a couple of years, nobody can buy diesel or gasoline-powered vehicles anymore for public transportation in many, many countries. But think about electric vehicle. Those, electrical buses. These buses usually run all day long, 200 to 300 miles a day. In order to be able to run all day long without charging, we have to equip around 300 to 400 kilowatt hour of battery on these buses. And I want to ask the audience to give me a wild guess. How much weight is that battery pack on that vehicle? For, let's say it's 300 kilowatt hour. Guess how much weight would you say? 1,000 pounds? Another guess? In fact, for that Tesla, with 100 kilowatt hour, it's almost 2,000 pounds, more than 2,000 pounds. So for that bus, you look at 3 tons. 3 tons is a lot of weight. We carry that weight around all day long. We waste a lot of energy by carrying that weight. And also the battery expensive. $100,000 to $200,000 has to be put to buy the battery. So can we address the problem like cost and weight, energy wasted basically, with wireless charging? Yes, it's potentially possible. The idea is that we're going to put all this wireless charging in bus stops. And then when the vehicle is driving in, as you can see, we start charging the vehicle, when the vehicle slows down. When people get up and down the vehicle, we charge the vehicle. And then until we move the vehicle out of that charging area. So it only takes like 30 seconds to get enough power to drive from one stop to another stop. By doing that, we can reduce the battery size by 2/3. So we can save roughly $100,000 of money on battery. We can save around 80 to 100 kilowatt hour of energy per day on one bus. If you have a fleet, you have a country, that's a lot of savings to get. So this is possible, but building those charging, of course, it takes time, and we have to invest the money. So this is the same. It's happening, but maybe slowly in a couple of years. Another example is to charge an electrical ship. Of course, electric ships is not popular yet, but people are building that. Charging ships is one of the problems. Charging ships is that this needs a lot of power, like in a megawatt. And having that megawatt cable, I can assure you, nobody can carry it because it's so heavy. You need 2 persons to carry that cable to charge an electric ship. That's number one. Number two is that you got water all over the place. And if you're not careful, there's salt water, something got there, and then you got a problem, like leak, maybe electric shock. So charging that ship with a dock, like you build this wireless charging transmitter, and when the ship docks close enough, it starts to transfer electricity. There's no worry about safety because it's not maybe on the ground, it's on a vertical surface maybe. So it's very safe, and there's actually a movie, I'm going to skip it. Another example is train and railway systems. And people ask, why do you need that? Think about fast train going all over the place. Well, it goes under a tunnel. Today, the trains are powered by overhead pantograph. So when train goes to a tunnel, the pantograph still has to work. So in order to make this tunnel to accommodate this pantograph, we have to make the tunnel big enough. That cost is huge. It's humongous. So if we get some sort of wireless power without a pantograph, when the train goes into the tunnel, we can reduce the tunnel size by 1/3. It's going to save billions of dollars for each tunnel. That's why you need it. So, example. Third example, we're looking at AGVs. What is AGV? AGV is called automatic guided vehicles. This technology is very popular in factory automation, in seaport, like Los Angeles, Long Beach, San Diego, wherever you see. These vehicles can be big as 50 tons, as small as just like little one in an Amazon warehouse. These little vehicles running around, some of them running inside a warehouse. You cannot have diesel or gas. On port, if you go to any seaport, you will be surprised, the smell. And I went to Long Beach Port twice. The smell is really bad because all the diesel engines are used. So nowadays, actually, the California Energy Commission is trying to get them to replace all these vehicles with electric vehicles. The problem is that these seaports are privately owned. They don't want it electrical. Why they don't want it? Because, first of all, electric vehicles are more expensive because of battery. Secondly, the batteries need to be charged. Right now, they can get a diesel within like a matter of half hour. But with electric vehicles, it takes 4 hours, 8 hours to charge. So for every diesel vehicle they replace with electric vehicle, they need to buy 2. The electric vehicle is twice more expensive or as expensive as diesel. So now they have to spend 4 times as much of money to replace one vehicle. Who is going to do it? You tell them, yeah, this is safe, this is good for the environment. Sorry, that's not my rule. Okay? So if we can charge these vehicles wirelessly, then the problem is solved because you can treat one-to-one. The vehicles are charged all the way when they're working, so only one vehicle to replace one vehicle. So that's cut off already cost. Secondly, we don't need that big battery anymore. So the vehicle becomes cheaper. Right? So then the price may be equivalent to those gasoline or diesel-powered vehicles. But of course, we have to spend money to build those wireless charging. So that's a different investment. So if the government is pitching in, like the Energy Commission again, they're putting money for the port saying, okay, I'm going to give you a match 1-to-1. So if you buy electric vehicle for $1, I'm going to give you another $1. So this will actually help promote this electric vehicle and wireless charging technology. I have a few more examples. Anybody know what this is about? The yellow stuff. This is called a bluefin underwater robot. You know, this bluefin is very actually, when I first time heard about it, I was really excited. This robot can go underwater, like maybe 1 mile, 2 miles deep, and they can handle the kind of pressure. And they can go around, do scientific discovery, and most importantly, they help with finding debris from, remember that Malaysia airplane MH370 that went missing, and they deployed this technology to look for the airplane potential debris on the seafloor. The only problem with this robot is that it has a battery, so it goes there, it takes time, half hour to get down, and they work there for 2 hours, they have to get them back to charge, and it takes another 2 hours to charge. So the work efficiency is about 40%. And not only that, because this thing has to go underwater to experience that high water pressure. And think about water pressure. If it's like 1.5 miles down on the seafloor, the pressure is enormous, right? Because every square meter, you get 1 ton of weight on that vehicle. So for 1,000 meters, that's 100 tons of weight. That's a lot of weight. So the charging port, normally this charging port on this, it will be crushed right away. So you have to have designed this system to be very robust, to be able to seal the charging. So our proposal is that let's build some wireless charging system on the sea floor, and that system can actually move with the ship. So when thing goes down to do its work, when its battery is finished, it goes back to the base to get charged. So it saves time up and down. And the charge can be very quick, like within an hour, maybe 2, because there's no manual handover anymore between unplug and plug and still the charging ports. So that'll work. So it can double the effectiveness of this system. Okay, next example, elevator. We probably, at one point, we have taken elevator to a high-rise building. Have anybody thought about it? You get the light inside the elevator, but the elevator is moving. How do you get the light? Where do you get the electricity? A cable. So most of the elevator today has a cable on top of the cart, or maybe at the bottom, either way. And for low-rise 2-3 story, it's not a problem. But when you have a story of 40 story, 100 story, that cable can be very long. When the elevator moves up and down, that cable starts to doing this. So it creates a lot of resistance. That's number one. It got efficiency, losses. And secondly, that cable is running up and down all day long, every day, 7/24. The cable can be damaged in a couple of years. They have to replace it. Expensive maintenance, things like that. So what we can do is we can build wireless charging in the hoist. Right? You have this transmitter, and then we have a battery, of course, on top of the cart, and then we have a receiver on the side of the elevator. So that when we move the elevator up and down, we also receive power. So we don't need the cable anymore. So that savings from the cable for high-rise building is probably can offset for the wireless charging. And also we reduce the maintenance cost for that whole thing. Okay. Another example is also interesting. And this actually comes from my own personal experience, because when I was doing my research about 30 years ago, I went down to this coal mining, like a couple hundred meters down there, and to look at how people are using these drills, this hammer, electrical ones, to collect the coal. The underground mining, one of the problem is what you call the gas. If you have spark, it's going to introduce explosion. So there's no plug, nothing under the mining area. So people have to carry 5-6 drills down in the morning and carry them back in the evening to get them charged. That's pretty heavy. So at that time, we don't have wireless charging concept yet. So later on, we thought, well, if you can actually, there's electricity there, but you just cannot plug and unplug things. So we have to get this device charged wirelessly down there so that people don't have to carry that many drills, only 2 per person, because one is working, the other one is being charged. So that's very easy. And some future-ish ideas may or may not work, we don't know. Like this one is charging the drones. Drones is very popular today. Actually, one particular application is already there. We have this overhead transmission lines. They run from San Diego to Imperial Valley, for example. They run above mountains and forest. Very difficult to get access to once they're built. But we need to inspect those lines once in a while to make sure they work properly. During fire season, we need to look at whether there's wire down or anything. So humans can hardly go there, so we fly airplanes to go. But this drones has a problem. They have limited range. So you cannot fly a drone from here for 20 miles, 30 miles. And so one way to get these drones recharged is to have all these platforms on these transmission towers. When the drone is inspecting the transmission lines, when they're about to run out of power, they go to these stations to get charged by themselves. And then continue to work, and then they work on a designed route, and they come back they send all these signals, they send all these results wirelessly to base station. So this is actually working. So, but of course, we have still to build those charge stations. This is probably going to become the next chapter for wireless charging. is that think about the pacemaker that I mentioned inside the body. Think about that man like with that eyeglass. You know what that is for? This actually technology is very exciting. Blind people cannot see the world. That's very sad. So people have developed, scientists have developed this eyeglass just like that we wear today. It's actually a camera. The camera can take pictures, videos in fact, not pictures. But that video is connected to an electrode inside the brain. And that brain, the brain nerve picks up the picture and translates it into an image that blind people can see. It's very powerful. It's very, very exciting. But getting that device inside the brain, I mean, we cannot just have an open hole here. We have to seal them inside. Again, that has a battery. We don't want to open the skull once in a while to replace the battery, right? So I think this thing might eventually have a wireless receiver that not only receive the video, but also receive power. Okay. And this is also interesting, is in space. When you have devices, satellites, when you have small drones that can work around the satellite, it's very hard to get those devices charged. There's power available because you can get power from a solar system, solar panels. But getting those devices charged is very difficult. You can't plug it in. There's nobody going to go there to plug them in, right? So the idea that to have this device, to have this solar panel, have these transmitters on certain flash service, and these little drones and satellites, they can all go there and get charged and continue to work for a long, long time. And this is even real idea that when we install solar panel, like the one that we just installed on our roof, it can generate electricity during the day when there's sun, but it won't generate when the sun is down. But in space, the sun is 24/7. You don't have to worry about cloud, we don't have to worry about nights. But that solar system, that solar panel, if we put it in the space, they generate a lot of electricity. We just don't have a way to get them down to Earth to use it. So people have said, well, maybe we are able to say, generate electricity, and then we create a laser beam. That laser beam can shine onto near Earth where we have a receiver, and then we can receive the power. Of course, this can be dangerous. So think about airplane flying into that laser beam. That's going to be dangerous. But again, this is very future-ish. We don't know what's going to happen, but it might work. Who knows? So finally, the thought is that wireless power transfer is an old concept that's been refreshed in the past just about 10 years, 15 years. And it's still evolving. A lot of things going on, like the animal detection, the foreign object detection is still under development. Safety is a concern. We don't want people, animal to get hurt. We also don't want to get like interference with our phones when we are near a wireless charging system. So a Tesla-free world, like what Tesla has dreamed, is not going to happen. I can tell you that. So, but special applications, like the ones that I listed, it's going to happen. Don't dream about driving a vehicle on a highway that it's going to pick up power anywhere. That's not going to happen. Economically, it's not feasible. Economically, it's not going to work. So for any system that is capable or is eligible for this wireless power transfer application, it's going to be a compromise between cost, safety, convenience, efficiency. Nothing's perfect, so we have to weigh which one is going to be over the other one. So we created a YouTube channel. We have a couple hundred videos on that channel. So if you are interested, welcome to go to that channel. We also publish some books on wireless power. So this is all work. But I also want to just explain to you in the next 3 slides what we do other than wireless power. So one of the recent research projects we have received from NASA is to work on a flying car or vertical takeoff and landing airplane. The idea of this one is if we design this vertical takeoff landing airplane, it's going to be better than a helicopter. The reason is that a helicopter is heavy, it's big, and it's noisy. It doesn't take a lot of goods or people, and it flies very slow. So this vertical takeoff and landing airplane, it takes off vertically and then land vertically as well, but it can fly very fast, about 300 miles per hour. So it doesn't need a runway. It carries more goods than people. It's not going to be for personal transportation anytime soon because we don't want to see all the airplanes flying around on campus at all. But it can be used for example, medical, emergency, rescue, special delivery, wartime delivery, things like that. So it's going to happen. So this project is very exciting. It gets a lot of attention. A second area we've been doing over the past almost 20 years is on battery safety. In every electric vehicle, there's a large battery pack. Battery has energy in it. And when the crash or the mismanagement, the battery can be dangerous. So people are still worried about that. So we developed battery management system to deal with, say, how to make the battery safer, how to make it live longer, all that kind of technology we've been working on. Any of these images that you see can be very disturbing for the electric vehicle car owners. Right? So we're hoping to improve that. And the last project we're working on, this is a project funded by the California Energy Commission, $2.8 million. We have been working into this project for 2 years, 1.5 years now. So when the electric vehicle is running for a couple of years, the battery is no longer good enough for either like acceleration, performance. You want to accelerate, it doesn't do the work for you. Or you won't be able to drive that long anymore. So the battery apparently is at its end of life. That's what we call first life. We can send the battery for recycling, but if we can get the battery to continue to work for something else for another few years, that can extend the battery life, reduce the environmental impact, and also you can help, like solar system, for example, to save money. That's going to be really cool. Right? So if you have your solar system, for example, it generates during the day, but it only generates when you go home, you need it, it won't generate anymore. But when you have a battery, we can store the energy when the solar is generating, and then we can use the energy when we need it. So that's where this energy storage system makes sense. So as the price of batteries go down, as the electric vehicle batteries, also the price at the almost like cost very little for people to deploy. So this is a project we're looking at, hopefully to be able to say whether this makes sense, and we can help to again save money for the owner and also help the environmental aspect of these electric vehicles. So with that, I want to thank you all for coming. Thank you, my students also for the hard work. Thank you, sponsors. And I want to thank my families for their support. And they're all here today with me. Thank you all for coming. And yeah.
Okay, here we go. Thank you for a phenomenal presentation. Really enjoyed it, learned a ton. We wanted to open it to questions from the audience. Anyone want to kick us off? Stanley?
Sure, go ahead.
Oh.
How much more expensive is the materials that go into a battery versus the materials that would charge a battery wirelessly?
When you wireless charge a battery, the battery cost is the same. Use the same battery. You get a receiver and transmitter. Yeah. So depending on the size of the system, for phone charging, for example, it really doesn't increase that much. But for electric vehicle charging, we're looking at about $2,000 for the whole system, transmitter and receiver for home charging.
Thanks.
Any other questions?
One of the things that happened with wireless communication is that there were wireless networks that weren't compatible. It wasn't until standards like IEEE 802.11, those standards allowed things to interoperate. Where in the automotive business are we in terms, is there an IEEE standard in work for wireless power transfer for automotive applications?
Yeah, you got to the point. the interoperability is going to be an issue. It's actually harder than the wireless standards. So there's one organization called the Society of Automotive Engineers, SAE. So they have worked on this for the past 15 years to develop a standard called SAE 2954, the wireless electric vehicle wireless charging standard. So that standard is already out. So they are talking about the size of the coil, receiver and transmitter, the distance, the location, and the communication between those. And also how to detect foreign objects like metal, animal, and so on. So there's an international standard. However, even with that standard in place, it is still very hard to have, say, a public, at home, no problem. If I buy a car, I buy the transmitter, right? It works for my car. But let's say if SDSU install wireless charging in certain parking lots, we want to make sure that charging will be able to charge whether the GM, Ford, Chrysler, Tesla vehicle. So that part is still being addressed. But there's organization working on that. Yes, Stan.
So Chris, I'm really interested in some of the future potential for this and where you think it is. In particular, thinking about pacemakers, right? So that has the problem of it's inside of a human, but the amount of energy it probably requires to function is probably much less than many of the other things. So how close do you think we are to having wireless charging for something like that that's so critical for human health?
Yes, you're right. So the wireless charging for body implanted devices are very small. They are in the milliwatts range. So to give you a perspective, our electric vehicle is charging at kilowatts or tens of kilowatts. A phone is charging at 5 to 15 watts. So, and the device over here is being charged roughly 10 to 100 milliwatts. So it's very small. And the distance can be as little as like millimeters, but it can be as far as like say a couple inches. But for implanted device, I think the idea is that going to have them close to the skin, where the device can be charged over say 1 hour or 2 hours. You can wear that device, or you can charge them while you're sleeping.
Regarding the power transmission efficiency between the cable type of charging and also wireless charging, what's the difference between those two? Because I think that is also a factor in the game.
You mean the efficiency, right?
The efficiency.
Yeah. So today, wireless charging can achieve almost the same efficiency as wired charging, almost the same. Slightly below, maybe 0.2 to 0.5% at the most.
Thank you.
I was going to ask you, how many students have you trained since you've been at SDSU?
Before I moved to San Diego, I worked at University of Michigan for about 14 years. And before that, I worked in China for another about 10 years as a lecturer. So if I just include the Michigan here, probably close to 100.
Incredible.
Yeah. And that doesn't include those undergrad students. I'm talking about graduate students.
Graduate level students.
Graduate and postdocs.
Wonderful, incredible, and I'm sure they're doing amazing work. Do we have other questions? Oh.
Just while we're there. Shasha?
Yeah. How have you been able to utilize the undergraduate and graduate students at SDSU in your work?
Very good question. Well, you know that the research is always done by students. So in my research group, I do have graduate students and postdocs, and I also work with senior design students or undergraduate students, like a few of them are here today. And the research apparently has different degree of depths. So the undergrad students are able to take, let's say, the fundamental part. So a lot of times you see, they're studying from textbooks, and then when they work on a project, so they can put them together and connect the dots. So I think undergrad students is a very important part in faculty research. So one of them I mentioned is the senior design projects. I guide on average about 2 projects every semester. The other is, of course, the university has this summer research fellowships, summer research scholarships, REU, that every summer university awards. I don't know how many, but a lot of them. So they pay undergrad students $4,000, $5,000, and they work with the faculty for 2 months. That is another avenue. We also, NSF, National Science Foundation, has this vast program of REU, and it's so popular across the country. We have it here too, but many of our students also participate in research at other schools for that REU program. Yeah, so I think many of our faculty, including myself, we are involving undergrad students in our research programs. Yes, Eugene.
What do you think is energy transmission and energy storage?
Yeah.
Energy transmission and storage, they can intuitively feel kind of maybe come on the opposite sides. So meaning that if you will have a breakthrough, let's say in energy storage, in the development of batteries, supercapacitors, something like that, will it negatively impact the projected success of the energy transmission? Will it diminish its value or not? What do you think?
I think they go hand by hand, which means, yes, I know many of you probably have already either driving or have access or look at electric vehicles. The battery for electric vehicles have evolved very quickly in the past just about 15 years. Lithium-ion batteries are quite a new thing. It was invented in 1992, and it took many years for that battery to be able to use for anything. So the price of that battery went down from about $2,000 per kilowatt hour about 15 years ago to today only at $150. So that price has gone down 10 times, like tenfold. So that is still developing. And also the energy that we can put in the battery increased not as much, probably double from what we have 10 years ago up to this point. But we are looking at also new battery technologies, such as solid-state batteries. And I think your research group was also looking at it earlier. The solid-state batteries are supposed to be safer because they don't explode, and also working better and having higher energy density. So all those things are also cheaper, maybe even. So all these things are going to help. Like we can put more battery in a vehicle because it's cheaper, right? So we can drive longer, so we don't have to charge them more frequently. And the battery will also last longer. But still, charging is still needed, whether you do wireless charging or wireless charging. So that's one I want to say. So wireless charging it's not going to be like diminished by that technology. On the other hand, you probably also have heard about this autonomous driving, which is very hot in the past couple of years. The autonomous driving is supposed to help us in many aspects. For example, people are envisioning that maybe in 10 years, we don't need personal vehicles anymore. Because if you can on your phone saying, I want to go from here to work, and the vehicle will come to your doorway in 2 minutes, and it drop you off at work, you don't have to park and walk a long distance to your office. Why would I need a vehicle? But that only happens when you have autonomous driving. So that autonomous driving vehicle needs to be charged. Who is going to plug it in to charge it? Right? So wireless charging here makes a lot of sense. So that vehicle will go to a certain area that has wireless charging. It will charge it itself, and it will move on to the next destination. So that's, I think, a lot of this are going to involve and they're going to develop, help each other. Okay.
Professor, I have
Yeah.
2 questions. The first question is, will wireless power transfer have any effect on the nearby wireless devices, especially in the case where you saw you have shown the elevator, the charging case of the elevator. So if there is a person inside the elevator using a cell phone,
Yeah.
will there be any effect of the transfer on the cell phone reception?
No. The reason is with this wireless charging, we always put shielding. So if you look at the receiver, there's a shielding on the back, so it's inside, it's okay. For the transmitter, there's a shielding on the back. So there's a field between the transmitter and receiver, but very little emissions around it. There will be some, but it's not going to impact the electronic devices.
Okay. And the second question is, you have shown the simulation for human being and animals.
Yes.
So I'm just wondering why there is difference between the magnetic field in both the cases. Is that because in one case the person was lying beside the vehicle and in another case the animal was?
Yeah. A very good question. Yes, I probably didn't make it clear. The human was next to the car, but the animal was under. So the animal is directly on top of the transmitter, a very strong magnetic field. We cannot shield it because that's how we transfer power. But the human is not able. I don't think anybody, even a child, can be able to climb on the charging pad. So that's why we didn't study it.
Because of the position.
Right. Because of the different of position, that's why there's much less electromagnetic field in a human than in an animal. Right. Yeah. Good question. Thank you. Yeah. Hi. There's another one.
Thanks, Dr. So I'd like to ask about the semiconductor technologies that you use in your research. Which ones did you use for the electronic devices, and which ones do you think that are good maybe for electric cars, and the others that are good for like low power?
Yeah.
Chris, do you mind repeating the question? It was hard to hear on this side.
I think I understood. Okay. Well, yeah, maybe other person couldn't hear, right? Yeah.
I'd like to thank Dr. Mee for his talk. I was asking about the semiconductor technologies that you have used in your research, and how do they differ, for example, for electric cars, which are high power, compared to low power applications like drones or like the small robots that they were working in factories.
Yeah. So he was talking about asking about semiconductor devices. You know, semiconductor devices are so amazing. I mean, we build things on silicon, which is all over the place. We have it in our backyards. So we have everybody near you. You will have semiconductor devices. So there are different semiconductor devices. So one that we use for like information for computers. Those are low power consumption devices. But for transfer power, we need those devices are fairly large. I mean, fairly large in comparison to the one that we use to transmit information. So the power device for wireless power transfer for high power, like for electric vehicles, buses, and others, they are today all called wide bandgap devices, like silicon carbide, gallium nitride, those devices. This is also amazing because those devices were developed only in the past 10 years. So they were fairly new as well. But for low power applications like cell phone charging, they just can use very simple like a silicon device, CMOS, for example, for low power applications. Yeah. Okay. And there's a question here. Do we? Oh, there's a question here. Okay.
Hey, how's it going, Professor? When we talk about the energy transition, a lot of emphasis is put on lithium-ion batteries, hydrogen, and hydrogen fuel, also renewables. But the big case with battery technology, WTI crude account $110 a barrel right now, accounts for I think 25-30% of the internal combustible engine for same transports. So when we talk about energy development in battery technology, the case can be made that mining and the rare earth metals for some of the mining development is very not economically friendly. And you mentioned about recycling. I just wanted to understand a little bit more about the recycling supply chain and where we see the emphasis needs to be put on recycling because as a consumer I know there's probably a ton of drawers in my house where I could probably recycle some batteries and reuse that rare earth to better applications.
Yeah. Well, I think your question was really including a few different parts. First of all, I think energy storage, the hydrogen fuel cell, like you mentioned, is not an energy storage device. It's a generator. It gets hydrogen and it generates electricity. So you still have to store that energy somewhere. Like hydrogen itself is energy storage. So when we have a solar, wind, and other renewable energy, one of the things that we have to do is to store them when we don't use them. So we can store them in a battery. That's one way. We can also doing electrolysis to convert water into hydrogen and then store the energy in hydrogen, then convert the hydrogen to electricity using fuel cells. So I think fuel cells, batteries, all these things are going to coexist for some time. They're going to compete to each other for a little while until someday that we can rule one technology over another. In terms of the life cycle of energy, like from crude oil, so there have been studies from well to wheels, which means let's get 1 gallon of fuel from well and refine them and then put in the tank, drive the vehicle, or we get that 1 ton of coal, let's say, we convert them into electricity in a power plant, transmit it into a house, charge it into a battery, drive a vehicle. So which one is driving longer for the same amount of energy from original source? All studies have indicated that electrical is still better. It's not definitely 3 or 4 times better, but it's probably say 5-10% instead of 2 to 3%. So that's still better. But when you talk about making batteries, I know there have been criticism saying, well, we make lithium-ion battery. Do you know where the lithium is coming from? And in Africa, for example, they have these mines. They employ underage workers, and so maybe not. It's good for our environment, may not be good for their environment. So I think there is a systematic study. There's a lot of papers, publications, and also white papers on those things. I think we're just, as a humanity, we have to get better to do one or another. So the Second Life EV battery project itself is to tackle one of them. Let's don't recycle them right away. Let's put them to work for us for another 5-10 years before we recycle them. So we can extend the life, help the environment, and also reduce the overall life cycle ownership. Okay? Yeah, I think there's one more question here.
Yeah. So one of the slides you talk about the vision that you use wireless power to launch flying objects like UAV. I'd like to ask you about how far the technology is right now away from that vision, and how efficient would it be, consider that we have to track and view, track the object and view the wireless power?
Yeah. So I think that's a very good question. I think I need to make myself clear. For the drone charging or the flying object, there are 2 ways to charge it. So one is to have a base. So the actual drone is not charging while flying. When it's almost done with battery, it goes to a base. It lands on the base, and there's a transmitter on the base to transfer power to charge that drone. That's one way. That's the most practical way that it's already existing today. Another way is people looking at shining like a beam of laser or something, and it tracks the drone when it's flying. That is also possible, but the efficiency is fairly low. I think the efficiency is about like 1% to 2%. So we're wasting most of the energy in the process of transferring this power. The distance, people have done studies as far as like 100 meters. Again, the efficiency is very, very low, less than 1%. Within about 5 meters, which may not have any practical use, you can get efficiency roughly about 10%. Okay.
Yeah, so for high power systems, Couldn't it build a lot of static in nearby pins? Is it dangerous for, if you touch anything that's going to build up a lot of static? I'm assuming the high power system is also technically a very high voltage.
I don't think I understand your question, sorry.
So, cell phones are not all that base station because the static, it can build static and it can spark. Similarly, the high power wireless transfer system, wouldn't it build a lot of static? Yeah.
I don't think I understand.
Maybe what I suggest, we were going to wrap up after this question anyway.
Yeah,
maybe you can take the time with
yeah.
Dr. Mi after to have the direct conversation about it. Thank you. Well, I want to thank you again and congratulate you.
Thank you. Yeah.
Please join me in congratulating Dr. Mi. Distinguished Professor Chris Mi. Congratulations.
Thank you very much.